Sir, hello. Hello, sir. Not audible.
Now, can you listen?
Yes, sir.
Okay, okay. Thanks for this update because I was speaking quite a lot. Okay. Okay, so what I was telling uh, that we have seen a multi-category uh, network which is trained for say number of classes, say R, and for that we need to take neurons in the circuit equal to number of classes. Suppose you want to learn 10 classes, then you will keep 10 neurons. So that is what I discussed earlier. And then you will train the neuron which is producing wrong answer. So we have taken one small problem which is of 3 classes. So for 3 classes, you can see here the desired response vector is of length 3. If I want to learn say 10 classes, then this desired response will be of length 10. Okay, so suppose in exam some 4 class problem is there, then you will observe that there are 4 positions here. What is dimension? Dimension is number of features that we are going to use for our problem. So this is x, say this is x1, this is x2, and this is x3. These are training samples. So that if I have 100 training samples, then I have x1 to x100 as my training set. Then there will be a test set. I can have xt1 to maybe xt100. Then these are some test samples. So we report the performance of a network on training set as well as on test set. So you can observe this thing in research paper. There are two things available, and mostly now people are reporting just test results. Okay, because in almost all the cases, training results are very good, maybe up to 100%, and then we have problem in test actually. So we have seen this, say we have this example with just three inputs, that is x1, x2 and x3. So augmented vector of that, we will call it as y1, and this as y2, and this as y3. So we are applying one by one to the network, and network will produce some output like this, because we have randomly assumed this weight. So this weight is randomly assumed, and we will calculate what is output of each neuron in that circuit. So there are 3 neurons. So we calculate output for each of them, and output is +1, -1, +1. But since my y1, that is input, belongs to class 1, I want +1 here, and all others are actually -1. So this has been rightly giving me, say, +1, but here it is -1. That is right, I want that. But here there is a wrong answer, so I need to train neuron number 3 only. These two are producing correct answers, so no need to train, no training. So you can see here, this is updated, and only third neuron is updated using perceptron learning rule. Then we are applying second input, and since it is class 2 input, my desired response is -1, +1, -1. By chance, suppose this was class 1 input again, then what will be desired response? Then it will be +1 here, and -1 here, and -1 here. Okay, so keep that thing in mind. Since this is a simple problem, you can observe what is going on. So this is class 2 sample. So I want here -1, +1 at second position, since my input is class 2, and third position -1 again. So you can see here, this is a wrong answer. So this was desired response. What is output? Output is +1 here, so which is wrong. +1 here, which is right. -1 here, which is right. So only neuron number 1 needs training. Okay, so we have updated here neuron number 1 weight, other weights are as it is. Then we took third input, which is belonging to class 3. So what is desired response for this? So this is -1, -1, +1. Okay, so based on what is current value of weight, I got +1, which is wrong, -1, which is right, and +1, this is also right. So only again neuron number 1 needs training, so that is updated. Other two are as it is. So like that, if I keep on doing, so maybe after 9 iterations, I got the correct answer, and the implementation or the weights of neurons are settled like this. Okay, so if I take this neuron number 1, just 1 second. If I take this neuron number 1, then you can see here what is input to this, or what is net value calculated here. This is equal to 5x1. Then second input is coming from this position, that is 3x2, and minus of 5. So -1 multiplied by 5, that is connected here. So here I am receiving net equal to 5x1 plus 3x2 minus 5. So if I put it equal to 0, that is my decision boundary. If net is greater than 0, then output is plus 1. If net is suppose less than 0, then output is minus 1. Okay, so since I want for class 1 output should be plus 1, so I am training accordingly. For rest of the classes, output requirement is minus 1. Okay, so the point where I cannot take a decision is that net equal to 0. So that is my decision boundary. So what is implemented by neuron number 1 is this particular line. So you can collect net of this second neuron, which is minus x2 minus 2 equal to 0. So it is implementing this line. And third neuron is implementing minus x1 plus x2 equal to 0. So these three lines are implemented by this circuit. So if I call this as net equal to this up to this, and net 2 equal to minus x2 minus 2, net 3 equal to minus 9x1 plus x2. Okay, this is actual implementation. So to fire neuron number 1, my sum must be more than 0, that is 5x1 plus 3x2 minus 5 is greater than 0, then neuron number is 1 is fired. Okay, so if we plot this and see the positive side of the line where the neuron gets fired, how to find out that? You can take the line equation, say 5x1 plus 3x2 minus 5 equal to 0. You collect the coefficients of the variables. So plus 5, so plus 5 plus 3. So that is somewhere this direction where neuron number is going to fire. So this is the direction. Okay, so this is the direction. So as per neuron number 1, anything above this is class 1. But that is not the region where class 1 will appear actually, because you will see that if you implement or if you draw regions for all the 3 neurons, then picture is different. So for this second line, that is minus x2 minus 2 equal to 0, if you plot this thing, so where is that? So this is the line minus x2 minus 2 equal to 0, and where is the positive side of this line? So you can see here we have drawn this positive side. So that is, if you collect the coefficients, so what is the coefficient? It is 0 minus 1. So 0 minus 1 is the direction. So if you plot that vector, so this is the direction of the second neuron where it will get fired. Now for third neuron, the direction is minus 9, the line implementation is minus 9x1 plus x2 equal to 0. So if you collect the coefficients, it will be minus 9 plus 1. So where is that? So this is the line minus 9x1 plus x2. So if you plot the corresponding vector, which is minus 9 plus x2, so minus 9 plus 1. So if you plot that, it is somewhere here. So this side is class positive side of this third neuron. So what we have done, we have collected all the positive sides of individual neurons Now you will see that for class 1, what is desired response? For class 1, desired response is +1, -1, -1. So this area, if you choose any point, this will satisfy all these three conditions. That is, only line number 1 or neuron number 1 is fired and other two are not firing. So can you check that thing? So let us remove this. Okay, so when I suppose stand here, what this line number 1 is saying? Line number 1 is saying whenever you are above me or this direction, I am going to fire. So neuron number 1 is going to fire since I am in the correct position. So this will produce +1. What about neuron number 2? Neuron number 2 is saying go this side so that I will be firing. So this side is not, so we are standing here, so I am standing in the opposite direction. So this neuron is not going to fire. Neuron number 1 is going to fire, neuron number 2 is not going to fire. So my answer for neuron number 2 is negative, that is -1. What will neuron number 3 will do? So neuron number 3 is implementing this line and it is saying that go this side. If you go this side, then I am going to fire. But we are behind this line, so we are standing here, so it will produce -1. So whenever I stand at this position, in fact, anywhere in this zone, I am going to produce this vector as output. So network will produce this vector as output, which is equal to the desired response for class 1. Okay, so this zone becomes class 1. Now suppose I am standing here, say input is from this side. What will happen? So input is suppose this side. Let us see what happens. So neuron number 1 is saying go this side, but I am in the opposite direction, so this will be -1. What neuron number 2 is saying? Neuron number 2 is saying go this side, but I am in the opposite direction, so I am here. Am I right? What neuron number 3 is saying? Go this side. So I am here. That is, I am in the right side. So this zone becomes class 3 zone. Okay. So like that, you can check for this zone. This is class 2 zone. So all these white portions are divided into 3 zones. This is class 1, class 2, and class 3. What about this shaded area? The shaded area is not giving you right answer. There are multiple positive or uh, incorrect answers. So this is the zone where you cannot really do the classification. Okay, you cannot classify data if it is falling in this shaded area, but you can classify your data if it is in this white portion. That is indecision region, that is you cannot decide really what is the class of this input. Okay, like that this network is working. So we have seen the training, and we can do using classical perceptron learning rule as well as delta learning rule. So when I use delta learning rule, the activation function must be continuous activation function. So that should be at least a tanh function or logistic function. So out any one of them you can choose and you can proceed. So homework is you can, if you try to solve this problem, uh, you try it using continuous activation function. What is the problem? You can take snapshot of this screen right now. I can clean this. So same problem we can solve using continuous activation function. So we have 3 samples belonging to 3 classes. Their desired response, this will not change. Desired response is this. Randomly assumed weights are same. Only thing is use delta learning rule for multi perceptron or multi neurons. Okay, that is the only change that I expect, and you try to solve. So when you go to continuous kind of perceptron, then you have to change your rule little bit. So same rule, but this f dash or o dash will come into picture, and accordingly if you use tan h or logistic function, you have to take into account this f dash quantity here. Okay, you have to change your learning rule a little bit. So you compute your output. Suppose output of some neuron is let us say 0.8, then how you will implement this? So this 0.8 will come here. Suppose desired response is +1, so +1 minus 0.8 into 1 minus 0.8 square, so that is its derivative. So this is its f dash value into input, say y. So only thing is you have to compute this term 1 minus o square extra. If you use this tan h kind of a function or logistic kind of a function, you have to do accordingly these changes. Now let us move now to the core of this subject. That is, we are now moving towards feed forward network multi-layer to be trained using back propagation. So this is the core of this subject, and this rule, that is generalized delta learning rule, you will find it is used heavily in almost all kinds of circuits till today. So even if it is deep learning networks, maybe of 200 layers or 300 layers and more, still people believe on this learning scheme. No doubt there are many modifications and some optimization techniques for faster solutions, uh, some ways of getting better results, so pruning methods, and so on. So there are many things that are happening, and one should start with this back propagation first, then rest you can understand very easily. So try to understand here onwards the concepts of uh, multi-layer, and then you can proceed. Even for language processing and all LSTM kinds of circuit, they use this back propagation or variants of this back propagation. Now why back propagation is required, or why we go for multi-layer? To understand that, we try to solve few simple problems. The first problem is called as a OR problem. So we know what is logical gate OR. You know that if I take 2 bits, then I have 4 possible combinations like this, and for 0 0 I get 0, and for anything, for any other combination I am going to get +1. Okay, so this is our simple OR gate or OR logic, I can say, in digital electronics or binary circuits. Now if I plot this 4 say combinations of inputs as features. Suppose I call this as x1, this as x2, or I can call it as ABCD, ABCD kind of thing. Then there are 4 points here, say A, then B, C, and D. These are 4 points. Then suppose I say this is class 1, and let us say this is class 2. Since output is plus 1 here, all of them are producing plus 1, and only this fellow is producing 0. So this I can call it as class 2, and I can call this as suppose class 1. So you can see here there are 3 points appearing as class 1 samples. So this is class 1, this is class 1, this is class 1. The 0 point is class 2. Now I can make a simple neuron which is shown here with weights 1, 1, and threshold here is 0.5. So this is my neuron with threshold equal to 0.5. So I am connecting my input here x and y, which is forming input vector, and this is 1, this is 1. Now whenever this input is not equal to 0, 0, so if I put 0, 0, then net value here is equal to 0 multiplied by 1 plus 0 multiplied 1. So this will be 0 in this case. So whenever my input is 0, 0, I will not get firing of this neuron. If I make any one of this input as 1, then net is greater than 0.5. Suppose I make this as 1 and this as 0, then the net value is 1 multiplied by 1, 1 plus 0 multiplied by 1. So this is equal to 1, which is greater than 0.5. So my neuron is going to fire. Okay, so this will happen for all these 3 inputs, and for this one, this neuron is not going to fire. That means I am implementing this particular line. What is implemented by this neuron is x, suppose, or in terms of x and y, I can write as x plus y equal to 0. So this particular line is implemented here by this neuron. And if I collect the coefficients again, then 1, 1 is the vector which is the positive side of this line. So 1, 1 is this direction. So anything in this direction above this line will produce positive answer, and below this it will produce say 0 or -1 answer, depending on what kind of neuron you are using. So that means I can solve, I'm writing here, I can solve OR problem using perceptron or a neuron. Then I can go for AND problem, which is another logic in our Boolean circuits. The case is like this. So 0, 0 output is 0, 0, 1 output is 0, 1, 0 output is 0, 1, 1 output is 1. So whenever both inputs are 1, 1, output is 1, otherwise output is say 0. So it's very similar case actually, but now these 3 are in one group and this lonely fellow is in say producing positive results. This is class 1 and the other things are in now class 2. Now we can use same neuron. I'm just changing the threshold to 0.1 from 0.5 to 1.5. Okay, so if I put 1.5, then you can check if I have 1 here and 1 here, then net value is 1 into 1 plus 1 into 1, so that is 2, which is more than 1.5, then neuron number 1 is going to fire and produce positive result. Now whenever I have other combination, my net is less than 1.5, so output is 0. So conclusion is, I can implement, or I can uh, implement this AND logic. Not I should write here neuron. A neuron can implement AND logic. So OR is done, AND is done. Okay. Now can I go further? Now we have this particular table. You can see here input is 0, 0, output is 0. Input is 1, 1, again output is 0. If input is 0, 1 or 1, 0, output is 1. So this is typical XOR table, which is also called as non-equality detector. Okay, so this is some typical XOR table. Now if I plot, suppose I call this as class 1 now, then these two things are class 2. So this 0, 0, this point is class 2, then 0, 1, this point is class 1, 1, 0, this is 0, 1 and 1, 0. So this 0, 0, this is 1, 0, 0, 1 and 1, 1. So this is again class 2. So if I have such a thing, then if I draw a line like this, so this side suppose I call it as class say 2, and this side as say class 1, or I can call this as class 2 because this is the only sample here, and this side I can call it as class 1. Then you can see here things are getting misclassified. Okay. I cannot draw a line which can separate these 4 samples into correct categories, like earlier case. In case of and OR logic, I was able to draw this simple line, single line, and this side was class 1 here, this side was class 2 for AND problem, and for OR problem this line was drawn, and this side is class 1 and this side is class 2. So when you look at this typical XOR problem, if I try to draw a line here, then this point is going to misclassify. If I try to draw a line here, then this point will misclassify. Like that, I cannot come to a line which I can draw and solve this problem in one go. That means I cannot use only one neuron and solve this problem. Okay, so this is a typical classical non-linear problem. So any new circuit, suppose you design your own neural network and you try to say that this is the best one, then people will ask you what is response of your circuit on typical XOR problem. So if you can solve this XOR problem, then you can handle non-linearity. So that is why people will ask you what is response on response on XOR data. So what is solution for this kind of a problem is I can use, say, two neurons to implement this line and this line. Then I say, okay, I have two lines now. I say this side of the line is class 1 and this side of the line is again class 1. So within these two lines, the zone which appears here, I will call it as class 2. Okay, try to understand this. What I have done, I have taken two neurons. Say this is neuron 1, this is neuron 2. So this is neuron 1, then I have another neuron 2. The first neuron is implementing this line and saying that go this side so that you will produce positive response. Okay, so this line implementation we can do easily. Then I can say I have another line or a neuron which is saying go this side. Okay, so both of them are indicating separate positive regions in the space. And you can see these squares are belonging to class 1 samples. This is class 1, this is also class 1. Okay, and these two things are class 2 things. So they are in this negative zone of both the lines. So this is the zone where class 2 lies and this is the zone where class 1 lies. Now for a given input, suppose I give you this input, try to understand this carefully now. Suppose I give you some input which is here and ask you to classify. What will happen? This neuron number one will say, okay, this is in the right position, this is positive. What this second fellow will say? It is saying, okay, go this side, but you see that this sample is in the opposite direction, so it will produce negative answer. So whenever you get neuron number 1 producing +1 and neuron number 2 producing -1, okay, actually it's a class 1 sample, because I know that this is standing here and this is the zone of class 1. Same thing will happen when I stand here. When I stand here, the second neuron will produce +1 and the first neuron will produce -1. Okay, so this will be the output of circuit here. And I know that since this is class 1 region, I will declare this input as class 1. In this common zone, this is the opposite side of this line and opposite side of this line, I will get -1 and -1. In that case, I will say it's class 2 sample. Now to decide if this is positive and this is negative, this is class 1, I require another neuron. Okay, so if you see this situation, that is +1 -1 as the output at this position, or -1 +1 -1 +1, any one of this combination, then output must be positive. Okay, otherwise if it is -1 and -1, output is -1. So I need to train this third fellow to observe what is going on here. Okay, that will tell me what is the correct class of given input. Okay, so we can go further. So I have a ready-made solution for you. So this is the implementation of what I said. So I have two lines here, two lines implemented by the first two neurons, say this neuron number 1 and this neuron number 2, and this third one to decide what is the actual output. So we will see this problem in detail in next class, and we will see one more problem. I will keep Monday's lecture for your queries. If you have any doubts, you can ask on Monday. I will take day after tomorrow's lecture. I will complete this part, and up to that you will have the things in your mid semester. Is that fine? Okay, let us stop.